So, it is our third lecture in the last week, in which we are going to talk about Ito's formula in higher dimension. What do we mean by that? See, if we have been talking about only, for example, stock price of one stock, interest rate, just one interest rate. Suppose I want to talk about two stock prices, I want to monitor two stocks at the same time and their prices and see how they are correlated, how their behavior is related to each other or not. What sort of approach I should need to analyze them? And then you have to talk about Ito's formula in higher dimension. In doing so, we need to talk about Brownian motion in higher dimension, that is a Brownian motion vector, that at every time t, the Brownian motion is not just a random variable, but a random vector. We have spoken about random vectors very briefly during our very first discussions of probability. So, this is what we are going to talk about, W1t, W2t. So, it is a d-dimensional vector if you assume at every time t. So, this is a higher dimensional Brownian process or Brownian motion, and it is consisting of d, say d components of Brownian motion, where each of them are random variables, each of them So, now the question would be why we need to think of such processes and what is the utility. See, you can still define a filtration adapted with Ft in the same way. Of course, when you are talking about Brownian motion, we will write Wt minus Ws, for example. These increments are independent, so Wt1 minus T2, Wt2 minus T3, T2 minus T1, so these would be having independent increments, in the sense that we really do not bother much about the vector, we really bother about its components. One important thing that you have to understand about the components is the following, that if you are talking about a component I and taking its quadratic variation, then this is just dt, and if you are talking about a cross variation of 1, then it is 0. Okay. So, that is what you have to keep in mind. So, when I is not equal to j, where I is not equal to j, then the cross quadratic variation is 0, and quadratic variation anyways dt is known to you. So, what we are looking at? We are essentially looking at not only one Ito process at the same Ito process, but we are looking at two Ito processes at the same time. For example, if you are looking at the price of two stocks, there are two stocks or two different Ito processes. So, we are trying to find relations between them. So, in general we are looking at Ito process. Suppose now we take d is equal to 2. So, we will now discuss we will just look at the scenario where d is equal to 2. So, basically we have two different Brownian motions, right, W1, W2. So, two different scenarios. See, the Brownian motion, the W function is not a unique thing, Wt is not unique. So, W1t and W2t are two different Brownian motions, right. W1t and W2t are two different Brownian motions, only that they have to satisfy the properties of Brownian motion. Their functional form need not be same. That is something which you have to always keep in mind, that these do not have unique functional forms. I mean, it can be depends on what sort of, it is a stochastic process which should follow certain pattern. So, if it just follows that pattern, it is a Brownian motion, not that it. So, there can be two different Brownian motions, right, and has very different sample paths for a given realization omega, but they are following all the properties of a Brownian motion, and hence they are Brownian motions. So, usually an Ito process. So, for example, we are looking at two different Ito processes. The first one is given by this formula, theta 1 u du plus 0 to t sigma 1 1. Essentially these are trying to recollect the some sort of a covariance type things or some sort of matrix. We will come to it very soon. You will soon see why I am writing like this. So, this every process xt that we are taking here is involving both the processes, is not just involving one process. So, it is some sort of a correlation coefficient sort of thing, and it is a function where you are essentially describing the first Ito process, but you are talking about the second Brownian motion. Similarly, you can write yt is equal to y0 plus 0 to t theta 2 u du plus 0 to t sigma 2 1 and 0 to t sigma 2 2. So, when you have two Brownian motions, so you can define these sort of processes, and then for example, I leave it to you to figure out what is xxt, that is what is the quadratic variation of this. So, of course, you can write the simple formula dxt is equal to theta 1 t du dt plus this w1 t plus this w2 t. You can write down the shorthands. So, using the shorthands you can come to this conclusion that if you take xxt, what will happen? Sorry, u. See, every time we are using what these sort of facts and whatever we had learned earlier, right, these shorthand notations. For example, if I want to write dxt, the cross variation, do not write the cross variation immediately as 0, basically you are multiplying of all the things. So, of course, I will not write to you what is dxt and what is dyt, you can write it out yourself now because we have been doing it so much repeatedly. Then this would turn out to be sigma 1 1 t sigma 2 1 t plus sigma 1 2 t plus sigma 2 2 t, this whole thing dt. Basically, if you want to write it like this, so it is not 0, you see. So, you want to write it like this. So, this cross quadratic process is a stochastic process given like this. So, I leave it to you to figure out what is the quadratic variation yyt. I am sure you can just immediately write it down without me telling you what to write. It is exactly the same thing with this, these things are replacing these things, that is all, the square of these things. So, once I know about this, I can write a 2-dimensional Ito formula. So, we are going to now talk about a 2-dimensional Ito formula, and then we will use it to study stock prices, two stock prices at the same time. In the 2-dimensional Ito formula case, we do not use a function just f t x, but f t x y, because here also we have to account for the process second detour process y. So, we are basically now considering a function of this form, and once I consider a function of this form, what do I expect? I expect that f t f x f x x sorry f t f x f y f x x f x y f y x f y y exist and are continuous. So, that is the assumption. This is an assumption. Okay, I have made this assumption. So, assumption. So, once I make this assumption, you know from basic analysis that f x y and f y x are the same thing. You can interchange, they are symmetric. Now, the formula is like this. The Ito formulas are basically stochastic Taylor's formula, Taylor's expansion. D f t x t y t is equal to f t t x t y t dt, plus with f x you will have the dx t term, f x t x t y t dx t. With f y you will have the dy t term. So, when if I had put w t here, w 1 w 2 say, then it will have w 1 w 2. So, f y again I should tell you all these inequalities that I am writing are in the almost surely sense, but these are random variables. But don't think that when I am writing f t x t y t, it essentially becomes a random variable. It is no longer just an ordinary function. You are writing an ordinary function, but you are then looking at its random avatar basically, you are looking at the random form of that. For example, if I take the function f x equal to half x square, you can write half capital X whole square, where x is a random variable. Because random variable at the end function, but overall behavior is slightly different. So, this is that is what I feel about random variables. These equalities, I understood that okay, this equality will hold with probability 1, so we do not bother much about talking about this every time. So, it just is an equality. Plus half x x t x t y t, with this you will have dx t dx t. Now, because f y x y and f y x are same, so we just write one of them. So, half of each will contribute a half term, so you will have a full term. So, say if I write f x y t x t y t dx t dy t. So, the cross one, which is this one, plus half f y y. I again tell you that f x y equal to f y y. So, basically I should have a term here half x y t x t y t dx t dy t plus half y x t x t y t dy t dx t, but both the terms are same. So, that half would give me 1. So, I do not write anything here. So, half of t x t y t, that into dy t dy t. So, this is, you see there is a pattern in the formula. With t there is dt, with x there is dx t, with y there is dy t, with xx there is dxt dxt, with xy there is dxy dxt, with yy there is dyt dy, there is a pattern. So, once you recognize the pattern, applying Ito's formula becomes a child's play, it becomes fun, you can just keep on applying and getting your results. So, you have to keep in your mind this pattern that Ito's formula gives you. Once you know this pattern, then everything is fine. Of course, proving this is a very different game, but it is better to first learn to use the pattern and learn to apply them. When we do the financial stuff, we will actually go and do that, we will see more of these applications. Now, let us look at the stock situation, two stocks, price of two stocks, and that will be important to know the price of two stocks and their behavior. But it is very important to know one of the theorems, it is called Levy's theorem. So, Levy's theorem tells us how to recognize a Brownian motion if there is one. It tells you that if you have a stochastic process mt with t greater than 0, suppose you have a stochastic process ft mt, it is given to you. So, this is a stochastic process mt with t greater than or equal to 0, that is given to you. Now, once you know that, suppose you have more additional information that there is a filtration ft to which this stochastic process is adapted and mt is adapted to it. Mt is adapted to it, and then additionally if you have the quadratic variation to be t, at time t it accommodates a quadratic variation of the amount t which is path independent, right. If you have this, then it implies M is a Brownian motion. So, this theorem is due to Paul Levy. It is always better to tell you some one or two stories about this guy called Paul Levy. Let us understand that Levy was really not a probabilist, he was an analyst, and in fact it was Rene Gatto, on whose name we have the Gatto derivative. Rene Gatto who started working on these sort of stochastic processes to look at them in a more detailed mathematical way, but he was killed in the World War I, and one or World War II, I am not exactly finishing that. So, one of the world wars Rene Gatto was killed, and then Paul Levy was told to see that his papers, what he has written, should be published. So, while reading what he has written, he got interested in probability and he himself became one of the leading probabilists of the 20th century, Paul Levy. So, the modern stuff about Brownian motion that we see, the modern theory and modern definition is essentially due to Paul Levy. So, it is very important to know the guy who had actually done stuff for us. Now, I give you a small homework. Thing is the following: take a specific ftxy equal to xy and then see what will you get. If you look at it, ftxy equal to xy gives you the feel of a product rule, that you are talking about xt into yt. When you are talking about d of ftx, you are talking about d of xt yt, you are talking about the product. So, what would the product be? How would the product rule look like? I would like you to finish it as a homework. Prove the following: So, you see there is always an additional term. So, it is not the standard calculus. So, it is always there is an additional term. So, you can apply this formula to this function to prove this, and this is homework. I think all the viewers, even if you do not give the exam, does not matter, but you should really try out this with your own to see that you are developing a gradual feel for applying the Ito's formula, not that you really have to prove things, etc., but just applying that. So, now I have two stock prices. I am analyzing two stocks. So, if I am analyzing two stocks, what should I look into? So, let us observe, let us just take correlated stock prices. So, let us just observe, or let us just say that I have two stocks of this particular type of behavior which satisfies the following stochastic differential equation. So, they are Ito processes of this type. So, this process only depends on the first Brownian motion, but now we will define a second stock price. This is an example, this is just example from Shreve, it is not that it is exactly everything has to follow like that. The second price, the second one depends on not only one Brownian motion, but of course, this rho 1 minus rho square has to be positive. So, rho has to lie between minus 1 and plus 1 with rho in minus 1 plus 1. So, this rho is some sort of a correlation coefficient. When there is an exact correlation, rho is 1, then this becomes 0. So, it just depends on W1t. And when there is rho is 0, that there is no correlation between W1 and W2t, that W1 and W2, then this S2 only depends on W2. So, that is what it is trying to capture. So, it is, so of course, you can have a more feel if you have a more knowledge about statistics, of course. So, depending on the rho, you know whether the processes are connected or not. So, here it seems to be that this process depends on W1t and W2t, but this W1, W2, there is, when you write this vector Wt is equal to W1 to W2 to Wt, each of these W1s, they are independent processes. W1 is independent from W2, W2 is independent from Wt. So, here the important thing to remember that W1 and W2 would always remain, this W1t and W2t are independent processes, they are not correlated here, okay. So, you are getting the Wt as W1 to Wt, that is independent process, but it does not mean that, but this process, maybe this process could be correlated to this, but they might not be independent. So, let me figure out, okay, so if I write this as some other Brownian motion, right, then this new Brownian motion, this whole Brownian motion may not be independent from this, but just W1 and W2t are independent. Then if that is the case, let us put W3t is this. So, I am making a new process, a new Brownian motion, and because all other properties of the Brownian motion would be satisfied, because you just have linear sums, does not matter, linear or combination. So, this is my new Brownian motion, it is a new process. Again, it is the Ito process, but it is a Brownian motion. Basically, I want to say that, okay, I want to have W3, this is nothing but rho W1t plus root over 1 minus rho square W2t. This is what I want. So I have made this new process, new Brownian motion. So this is the differential form of this. Okay. So what I will now show essentially, technically I am writing that this is the differential form part, but one has to show that, see now one has to show that if I take W3T like this, that dW3 would actually be like this. Now I had just written it down because that is what will come, that if W3T is chosen like this, then dW3T would actually be this, and there will be a correlation then between W1T and W3T. You can compute the covariance, and that is why we just start looking at how to do the stuff. So if you look at the covariance, look at dW3T into dW3T, then of course dW3T is this one basically. So what I am trying to say is that if you look at it, so what I have done, so basically I have now replaced this by dW3T. So my S2 now depends on some other Brownian motion, which is a combination of W1 and W2. So here you have W3T, if you take, it will come out to be dt, and I want you to really do this calculation. Is just basically, if you look at it, it is nothing but rho square dt plus 1 minus rho square dt. So it turns out to be dt, because this is the quadrant. If you do cross, dW1 dW2t is 0, so that is why that cross variation becomes 0. So you have to take only their quadratic variation. So their quadratic variation is rho square dt plus 1 by 1 minus rho square dt. So this turns out to be, so the quadratic variation is t for this, and hence here W0 is 0, Wt is greater than or equal to 0. It is adapted, it can be adapted to the same filtration, because if I have full knowledge of W1 and W2, I have full knowledge of W3. It can be adapted to the same filtration as W1, W2, the vector W, and then W3 is satisfying this for all t. So the quadratic variation accumulator up to time t is t, and hence by Levy's theorem W3 is a Brownian motion. So though we had been telling that okay, W3 would be a Brownian motion, it is very intuitively clear that things can just be transferred, but you see, to mathematically to be rigorous, we have to apply Levy's theorem here to show that it is truly a Brownian motion. So that is why I have written the Levy's theorem up there, to show that it is truly a Brownian motion. So basically what you have now is that you have written d S2t is equal to alpha 2 S2t plus sigma 2 S2 dW3t. So are these processes now independent? Are the stock movement of stock price 1 and stock price 2 are independent of each other? They do not depend on the price of the other. In fact, they are independent to the extent, they are not independent because we can show that there is positive correlation, there is correlation, the covariance between W3 and W1 is not 0. Though their means are 0, but because covariance is expectation of xy minus ex into ey, you can show that the covariance, which I am not going to calculate, actually you can show that expectation of W1t into W3t is actually equal to rho t. So you have a non-negative for every t unless t is greater than equal to, for all t greater than equal to 0, right, you have a non-negative correlation coefficient, you have a non-negative covariance, you have a non-negative, sorry, you have a non-zero covariance. So, there is a relation between this and this. So, when you have two stocks, you are essentially looking into a scenario where the stocks price movements can be related to each other, correlated to each other. It is not that one price is going in some way, another is going in certain way, they are independent of each other. They could be independent of each other if you possibly had just W2 here, then they are independent. But once you involve, say, this sort of the multi-dimensional, if both of them are multi-dimensional Ito processes like what we had done, then stock price can get correlated. So, that is a much more difficult situation, and in finance we tried, that is something is slightly difficult to study, and we will study it when we will talk about finance separately, separate course in finance. So, okay. So, thank you for listening to the third lecture, and then we are ending, culminating in the last two lectures, which is on the Black-Scholes equation, for which most of you must be waiting, and I had myself learned all these things in the Black-Scholes equation. And I would, in this lecture, I would ask my TS to come up and join me, to at least they should be able, one should be able to see who are their TS. Please come up for a minute before we start the Black-Scholes lecture. Come on. So, here is Prashant Jha, who is a PhD student in mathematics, who is working in statistics actually, and she is Poonam Kesarwani, who is also a PhD student in mathematics working in optimization theory, and both seems to have some good idea about statistics. Maybe at the end of the course, after 5th lecture, they can say their own opinion about how they have liked or enjoyed the course, and we can end that. So, at least the viewer should be able to see with whom they are interacting. So, that's quite important. So, it's very important to see the person with whom you are interacting, then things get much better. So, thank you. Go ahead. So, we will start the 4th lecture after some time. Thank you.